Welcome to the next session. In this session of small signal operation and models, so we will derive what are the expressions for voltage gain, and also we will see how to write the small signal equivalent circuit for the MOSFET amplifier circuits. So therefore this discussion includes deriving voltage gain and small signal equivalent circuit models. So here, considering the circuit shown in the figure, we are interested in finding the voltage gain for this amplifier circuit. You just observe what are the voltages that are marked here at the different terminals. So here we have the VGS. Okay, so VGS is nothing but our input voltage, and also VDS is nothing but our output voltage available at the drain terminal. So now just observe the notations also. So as we have been discussing, small v capital GS, it includes the total voltage, that is it is the sum of VGS, that is small signal VGS, plus the DC bias capital VGS. So therefore here the instantaneous input is available between gate and source terminal, and now you can consider that this small v with capital GS suffix, okay, so as the input signal. So here I'll write VGS as nothing but the input voltage, okay. Similarly at the drain terminal, so we have VDS, okay, so this also represents the instantaneous output. So this VDS is the result of both, in the sense it includes both the DC conditions plus the instantaneous signal superimposed on that. Okay. So therefore when we are deriving the voltage gain, so then we know that the voltage gain is nothing but the ratio of output voltage to input voltage. So therefore now in this a particular circuit, okay, so we need to identify, or we need to substitute which is the output voltage term and which is the input voltage term, okay. So obviously, so here VDS is the output and VGS is the input, okay. So therefore now we need to derive, so how the AV or voltage gain of this amplifier circuit can be expressed in terms of the circuit components. So as well as, is it possible to include the transconductance factor also, okay. So therefore let us derive an expression for the voltage gain AV of this circuit diagram. So first I will write the expression for VD at the drain terminal. So at the drain terminal, and write VD is equal to VDD minus RD into ID. Okay. So now under small signal condition, we can write this VD as nothing but VDD minus RD into ID is nothing but capital ID and small ID. So that is capital ID is nothing but because of the DC biasing condition, and this small I small d, this is the signal component, okay. So VD or VDS, okay, so you can write either VD or VDS, both are same, as source is grounded, okay. So next it is VD minus RD into ID, okay. Next, the signal component of the drain voltage, okay. So signal component of the drain voltage, we have to write as V, small v, and suffix is small d, that is it is only the signal component, that's all, excluding the DC conditions. So therefore this will be minus ID into RD, but ID is nothing but minus GM into VGS also, this into RD, okay, because we have the relation for transconductance, which is nothing but, okay, so GM is nothing but the ratio of ID by VGS. So using that, it is possible to represent VD as a product of GM, VGS and RD. Okay. So therefore, using this equation, now the voltage gain AV can be written as VD by VGS. Okay, so VD or VDS both are same. This will be equal to minus GM into RD. So this is the expression for the voltage gain AV in case of MOSFET amplifier circuits. Now this picture shows the instantaneous VGS and VDS values. Okay, so just observe the first picture. So where on the y-axis we have small v GS, so that is the instantaneous values. Now why it is instantaneous, you can see that we have a certain DC level which is marked as capital VGS. Okay, so this is the constant DC established by the biasing circuit. On this we have superimposed the small signal. Okay, and what is the condition of the small signal is, so if its peak to peak amplitude is V, then that V by 2 should be very much less than 2 times of VGS minus VT, and this condition we have seen while deriving the signal current in the drain terminal topic. Okay, so therefore the first picture, it represents the instantaneous VGS voltage. So now after amplification at VDS, when we measure the amplified signal, so you can see that the same signal is available in the enlarged version, and here the enlargement factor, that is magnification factor, is nothing but by GM into RD times the V is increased. Okay, so therefore the overall peak to peak amplitude available for the signal at the drain terminal will be GM into RD into V. And also the conditions for the proper amplification here is, the maximum value of this instantaneous VDS voltage should be less than or equal to VDD, that is supply voltage, and also the minimum voltage of this instantaneous drain to source voltage on the lower side. Okay, so it should be greater than or equal to VGS max minus VT. Okay, so for these two conditions there will be no clipping and a complete signal will be available in the amplified form at the drain terminal. Okay, and this VDS is nothing but the DC biasing voltage setup in the amplifier circuit. So therefore this is regarding the AV expression, voltage gain expression, which is nothing but minus GM into RD, and representation of instantaneous values of VGS and VDC through this graph. Now concerned with this MOSFETs, okay, so we have another important concept called small signal equivalent circuit models. And now from the signal point of view, okay, so we have seen that the MOSFET behaves like a voltage controlled current source. So what is that voltage which is controlling the current source? Is nothing but gate to source voltage VGS. So whenever VGS is varied, it varies the drain current also. So therefore the output current available at the drain terminal is directly under the control of the signal voltage applied between gate and the source terminal. So thus MOSFET behaves like a voltage controlled current source. So current at the output terminal varies when voltage between input terminal is varied. Now here between gate and source, okay, so what we find is that terminal accepts the small signal VGS, and at the drain terminal the circuit provides a current GM into VGS. Okay, and also for these circuits the resistance of the controlled source is very high and the output resistance is also very high. So combining all these different factors of the MOS amplifier circuit, okay, so the circuit model can be drawn in which the MOSFET is replaced by its small signal equivalent. Okay, and that circuit is known as the small signal circuit model or small signal equivalent circuit. Okay, so therefore that small signal equivalent circuit will contain all the information about the device, that is it is going to include at the input side, that is between gate and source, the input signal conditions, as well as between the drain and source terminals. It also includes the output current information. At the same time, it also includes the output resistance also. Okay. So therefore, in the next session we will see how to draw the small signal equivalent model, and also we will derive the transconductance parameter of the MOSFETs. Thank you.